Yeah, I'm Jonathan Stone from the Lucasfilm Advanced Development Group and from various projects in the Academy Software Foundation. And I'm really proud to welcome you to the MaterialX and OpenPBR virtual town hall. I believe this is our fifth such event since we joined the ASWF back in 2021. It's really amazing to see how the community has grown and how the project has grown since then. For today, we have these seven presenters. This is a really great lineup. There'll be some cool announcements and some surprises. So hopefully, folks will be happy they joined us live today. First, I'll give some updates for the MaterialX project over the past year. Then we'll have Adrian Arubel from Autodesk giving updates on the OpenPBR side, followed by Fran Gonzalez Garcia from Pixar, talking about some new work to add the MaterialX BSDF nodes to RenderMan XPU. Then we'll have Johan Bold from IKEA talking about their use of shader translation graphs in their content pipelines. Followed by Arnon Marcus at Otoy talking about the latest work in Octane 2026. Then Frankie Liu from NVIDIA talking about the latest work in NVIDIA Omniverse. And then we'll wrap up with Ashwin Bhatt from Autodesk talking about the latest work in their various tools and pipelines. So just to give a quick update on the MaterialX project itself, um, one of the big uh, one of the big updates for this past year is we actually had two major releases. One is 1.39.2, which built upon work from last year, and that brought a bunch of new visual features to MaterialX, including the Chang-Hair BSDF contributed by NVIDIA. You see it in the upper right. Generic color ramps contributed by Autodesk in the lower right. Improved Worley noise from side effects. We now have a proper shading graph for the Disney principled shading model. That's cross-platform and works in all shading languages. And we had a ton of shader generation optimizations as part of that release. Then that was followed quickly by MaterialX 1.39.3. This one was more focused on the collaboration between MaterialX and OpenUSD. So there was a bunch of work to align releases between our two projects, making sure that the latest MaterialX would be the default in the latest USD. And that occurred in USD 25.05. And we're aiming to maintain that alignment as well as possible going forward. But this is the first time that MaterialX 1.39 is available in USD by default, which provides access to OpenPBR Surface and a bunch of more modern BSDF nodes such as Aeon Diffuse, Zeltner Sheen, and Hoffman Schlick. So we're really excited about that one. Then I also want to highlight ASWF Dev Days. This is a really important event for all of our projects, but we're really proud of the collaborations that we've done with new contributors to MaterialX. For those who don't know, ASWF Dev Days is it's a time when we provide dedicated mentorship to new ASWF contributors, where the senior leadership of each team helps to make sure that folks can get up and running, working usually on a small project that takes 1 or 2 days. In the past two events, we merged over 20 contributions to MaterialX, and we're really excited with all of the not just the new work in the project, but also the new community members that have joined. We'll have another ASWF Dev Days event on September 25th, and there's a link below if you would like to join and become a part of that. Then I'll just note this is a brief overview of upcoming work. One thing that's important to highlight is we have a release candidate out right now for MaterialX 1.39.4. This also has a ton of new features and optimizations. I won't talk about them here because our other speakers today will talk about their part in adding those and how they have been integrated. But it's a lot of cool new work. Going forward, we're also excited to integrate the new nano color spaces into MaterialX. That's a collaboration with the Open Color IO project. And we're also excited about some new work to integrate slang shading code generation into MaterialX, allowing you to generate slang shaders directly from MaterialX graphs. We feel that's an important step forward to allow inverse rendering and machine learning based on MaterialX content in a straightforward way. And then finally, I'll just put up this slide with a bunch of links on how you can join the conversation if you'd like to participate, either as a new developer or a senior developer already on a team. And again, I'll note ASWF Dev Days. We're having another event in September. With that, I will hand it over to Adrian Arubel to talk about updates on the OpenPBR side.
Hello, thank you, Jonathan. I'm Adrian from Autodesk, and today I'll be talking about OpenPBR. So I'll start with a quick overview of what the OpenPBR project, if you haven't followed that closely. Then I'll talk about what we did last year, talk about the current work effort and what comes next, and then I'll finish about the plug with the various SIGGRAPH events that we'll be attending this year. So in case you don't know, OpenPBR was officially released last year in its first official version. It's a new surface appearance model, or Uber shader. It's meant to be physically based by default, and it has an artist-friendly parameterization. So it originated as the synthesis of Autodesk Standard Surface and Adobe Standard Material. It has an open governance as part of MaterialX and the Academy Software Foundation, and it's backed by software vendors, hardware vendors, and studios. The project is really a specification that is written for implementers with precise description of the expected appearance and a parameter reference, as well as a reference implementation in MaterialX. So over last year, we've had major contributions from Autodesk, Adobe, ILM, Apple, Epic, NVIDIA, Side Effects, and many others. And I want to thank all the contributors for their hard work. If you're interested in contributing to the project, we use the usual GitHub workflows, even if it's a specification, like a document. You can post issues, propose PRs. We have a very active Slack channel with very interesting and deeply technical discussions on BSDFs and appearance on the Academy Software Foundation Slack instance, and a bi-weekly meeting alternating with the MaterialX meeting. So in last year, after finally delivering the first version of the specification, we really all kicked into gear and focused on delivering high-quality implementations and tweaking the spec to address the issues that appear as the number of implementations grew. So OpenPBR is now available in USD24, USD25 through MaterialX, as well as multiple DCCs, and more coming, as you'll hear in this session. We're also working on the bug fix version of OpenPBR. We follow semantic versioning and release bug fix version that do not affect the look by only fixing issues in the spec. And if we want to affect the look, we increase the version further. And it's what I'm going to talk about right now, because we're currently very busy working on OpenPBR 1.2, in which we plan to introduce new features, improve correctness, address user feedback. As this version will change the look in specific use case for what we hope is the better, we plan on making it easy to use OpenPBR 1.1 and 1.2 concurrently. And the idea is that the standard will evolve while maintaining compatibility. So I'll go in details over a few proposed improvements for the 1.2 version. And for each improvement, I'll point at the GitHub PR where those changes are discussed if you're interested in the nitty-gritty details. So one of the new improvements we plan on introducing are specular haze controls to better represent dirty or smudged reflective surfaces and improve the artistic control of the specular tail. Those would be two new controls, one to control the spread of the haze and one to control the intensity. And in practice, this could be done by mixing two BSDFs. And here are three wages varying the haze and the spread on a smooth metal base. And this is a different effect from coating. It increased the number of possible looks, which is what we're after here. And this was implemented following user feedback, as artists were used to tweak the coat on solid surface in a non-physical way to achieve something close to this. It's also a feature commonly available in other Uber shaders. Another improvement is retroreflective materials, and those are ubiquitous in real life, and there's a strong interest in being able to represent them without resorting to tricks such as tweaking normals in OpenPBR. And in this proposal, we want to introduce a modification to the microfacet BRDF and not a new BRDF completely to make them optionally retroreflective. And this is a joint effort by Autodesk and NVIDIA and should also be made available as a single brick inside MaterialX. And you can see the effect at various light angles on smooth and rough retroreflectors. This change is interesting because that's one thing that users found not immediately intuitive in OpenPBR. It's the ways the specular weight affects refraction. So in the specification, the specular weight affects the IOR to affect the reflectivity instead of simply dialing down the reflective lobe. And this gives a much nicer and physically plausible effect. But it also has a side effect on the refraction, as the IOR of the refraction and reflection are coupled. So we propose to decouple the effect of specular weight, so it only affects the reflection IOR, and you'll understand better why. So this is an iteration of the issue on the glass surface, where lowering the specular weight reduces the IOR and makes the glass more transparent, where the intended effect would be closer to what we propose on for OpenPBR 1.2 and simply dial down the reflection while maintaining the nice properties that we have on specular weight. And the last example of the 1.2 proposed changes I want to talk today about is a better way to model how the roughness of the top layer affects the roughness of a base, and have a slightly easier image to understand this. So the top wedge shows that the rough fuzz doesn't affect the metal base at all. The reflections stay sharp, and users complain that they have to manually dial up the roughness of the underlying base to achieve a realistic look. So we want to avoid the unrealistic effect, and we want to avoid manual steps as well. So we propose a new roughening model where the roughness of the top layers, such as fuzz or coat, correctly affects the roughness of the base. And now an announcement. So we are finally very, very happy to be able to publicly talk for the first time about an initiative we've been working on for the past few months, which is OpenPBR Volume. This is an additional appearance model for volume assets as part of the OpenPBR project. Volume assets such as clouds, smoke, fire, explosions are ubiquitous in production, and there's a strong need to be able to exchange and transport appearance for those assets and to make it easier to achieve interesting looks. So as same as with surfaces, coming with a good Uber shader for volume takes a lot of knowledge. This is a collaboration between Autodesk and SideFX. And we're working on combining the strength of the Houdini Pyro and the Arnold standard volume shaders into a new model. And this is very much a work in progress. It's not yet public. Our goal is similar to the OpenPBR surface goals. So we want to achieve an open specification describing appearance and parameterization, and a MaterialX reference implementation. And if you're interested in this project, do reach out to the OpenPBR project. So yeah, to summarize what the OpenPBR project is working at the moment, OpenPBR 1.2, improving real-time implementation, which is a very important topic to a lot of the members, including us. And as mentioned, we want to push beyond surfaces with volumes and hair. And finally, we'll be talking about OpenPBR a lot more at SIGGRAPH. So if you're around, come talk to us. We'll be presenting on the first session of DigiPro on Saturday. We'll have a very technical deep dive session during the physically based shading in theory and practice course on Sunday. We'll have a community BOF on Monday, and there'll be panels at the Adobe Substance Day on Monday too. Thank you all, and with that, I'll hand it over to Fran for the RenderMan update.
Hopefully my slides go through well. So yeah, so hi everyone. Sorry, there you go. Okay, so hi everyone. Thank you, Adrian. I'm Fran Gonzalez, Senior Software Engineer in the RenderMan team at Pixar, and today I'll be walking you through how RenderMan XPU now natively supports MaterialX PSCF nodes, and how this work is a result of a close collaboration between Pixar and Lucasfilm. So this presentation, basically, we're going to start with a quick introduction, then talk about the collaborative work between our teams at Pixar and Lucasfilm. After that, we'll dive into the details of MaterialX PSCF support in XPU and discuss its integration in production workflows, and wrap it up with what's coming next. So first of all, for those of you that don't know, RenderMan XPU is Pixar's next hybrid rendering architecture, and it has built to fully leverage both CPU and GPU devices to accelerate production path tracing. It was designed from the ground up to meet the demands of feature animation, where complexity and scale are basically the norm. And with XPU, artists basically get the best of both worlds. On one side, they get fast, responsive, interactive workflows. And on the other side, high quality final frame rendering, all within the same system and rendering architecture. In terms of materials, RenderMan XPU supports a wide range of BXDFs, including Pixar Surface and the principal Disney BSDF, among others. And specifically, Pixar Surface is our Uber shader with many different lobes, and it has been used at the studio for many years in productions like Toy Story, Inside Out, and the most recent Elio. In recent development, we have extended material support in XPU to include MaterialX Llama by implementing nodes like MaterialX Llama Conductor, Dielectric, Subsurface Scattering, along with combiner nodes like Add, Mix, and Layer. And this process of supporting MaterialX Llama has been a key step towards open standards for us, and it leads us to MaterialX. So why MaterialX for RenderMan XPU? So first of all, as you probably know, MaterialX is an open platform independent standard for material descriptions. And of course, within the RenderMan team, we are super interested in all this stuff. Second, the goal of MaterialX is basically to enable material interchange across DCCs and renderers and applications, making workflows more unified across the industry. And last but not least, in RenderMan, we already support MaterialX Llama, as I already mentioned. So it was a no-brainer for us to start thinking about supporting MaterialX, specifically through the BSDF nodes, which is where the real shading logic happens. To make this project and MaterialX BSDF nodes a reality in RenderMan XPU, we've been working closely with our colleagues at Lucasfilm. Both of us basically share the same goal of unifying shading standards across the Disney productions. And this collaboration has been instrumental in defining how MaterialX BSDF nodes are implemented in a way that's first artist friendly and second, and really important, to production ready. So the goal was clear since the early stages of the project. We wanted to support arbitrary combinations of MaterialX BSDF nodes with physical correctness, good performance on both devices, CPUs and GPUs, and a native integration into RenderMan XPU. To do so, we achieved this by treating MaterialX BSDF nodes just like any other BXDF in XPU, like Pixar Surface. What this means? So for MaterialX BSDFs, they needed first to be implemented as external plugins, as any other BXDF in RenderMan XPU, to make it easy to expand and extend the renderer in the future. The same core kernels from those BSDF needed to run on both CPU and GPUs, sharing most of the code across both devices. And we needed to make usage of custom OSL closures that we generate to represent each BXDF directly in OSL. So as a consequence, all of that work, we currently have native support of material BXDFs in XPU. And here you have a set of renders using some of those BSDFs applied into our lovely chipbots, of course. And here you can see an example of ordinary diffuse, Burley diffuse, generalized slake, or sheen, to name a few. And here you can also see another example of a more complicated scene using MaterialX BSDF nodes, showing how material BSDFs are now first-class citizens BXDFs in XPU. And one important note here is that all of this work has been achieved and possible by sharing most of the core code between MaterialX and MaterialX Llama BSDFs. I would also like to mention that we have already implemented early support for combiners and utility nodes like Add and Mix in RenderMan XPU, which allow artists basically to combine different BSDFs. And currently support for the layer node is a work in progress. And as an example of combiner nodes or utility nodes being used within RenderMan XPU and with MaterialX BSDF nodes, here you have the Sterling scene on the right, which is the result of mixing the two different materials shown on the left with the same weight for both. So up to now, I have shown you results of MaterialX PSDFs being used with RenderMan XPU. But I would like to emphasize that these nodes are also being integrated in real production workflows or DCCs like Solaris or LookDevX in Maya. For instance, in Solaris, we already have an early prototype of RenderMan XPU working with MaterialX PSDFs via ATPRMan. And we also began the work that needs to happen to support MaterialX standard surface. And this video is just a snippet of that early work. So looking ahead, our main goals are basically first to finish the support for layering nodes through the usage of the layer utility node. Second, complete full standard surface compatibility for RenderMan XPU. And third, we're also preparing RenderMan XPU for OpenPBR adoption via MaterialX. To wrap up this presentation, the takeaway messages from it would be, first of all, MaterialX BSDFs are now fully integrated into RenderMan XPU. They enable physically correct, artist-friendly shading that works seamlessly across CPU and GPU devices. This work was a joint effort between Pixar and Lucasfilm, and a step toward truly interchangeable shading across tools and studios for us. And in closing, I hope that guided by the principles of performance, scalability, and openness, this work done by our friends at Lucasfilm and us will contribute meaningfully to unify how we describe and render materials in the years to come with RenderMan XPU. And thanks for your time. And with all that said, I'm going to hand you over to Johan from IKEA.
Johan, you're muted, I guess.
Awesome, thank you very much. I was so focused on sharing the screen. Thank you, Fran. Hi, my name is Johan and I work at IKEA Marketing and Communication as a 3D technical developer. In this talk, I will tell you how we optimize our workflows using translation graphs. So IKEA sells furniture, and we currently have around 20,000 articles listed at our webpage. Most of our articles have been sold for a while, like Billy, which is still sold today and was introduced in 1979. And each article tends to have rendered content, such as images and videos, but also real-time 3D models. So we need to support a lot of articles for a long time where the deliveries have a wide range of constraints. And I want you to meet the storage bench in the new Omgänger range. This is one of the first USC MaterialX assets we have created. And here's a ray traced image using the same third-party renderer we use for most of our rendered content. And in this talk, I will tell you about translation graph. So what is a translation graph? In MaterialX, there are different shading models implemented. And the translation graph is a shading network which transforms the input of one shader model to another shading model with the goal of providing as similar results as possible. So how can we use this to reduce double work? When creating a new appearances, we only want to create the high fidelity version of the shaders which will be used for offline rendered content. For real-time materials, instead of manually creating a real-time version, we're using the standard surface to GLTF PBR translation graph, reducing the number of shaders our material technicians need to create. And after translation to GLTF PBR, we bake each input to a texture and use these textures in a GLTF model. These GLTF materials can be used as a real-time library. However, when baking down a complex shading network to a single texture, there can be issues with tiling or texture scaling. To avoid these issues, we can bake straight to a 3D model. And our approach is a three-step solution, where we create a decimated 3D model and a set of texture containing mesh attributes such as positions, text chords, normals, material IDs. And the second step, for all materials used in the model, we translate them from standard surface to GLTF PBR and generate OSL shaders. And using the texture with the material IDs from the first step,
we, for each pixel, pick the corresponding OSL shader, populate the shader globals using the other mesh attribute textures, and then shade that pixel. And when baking is done, we get a set of textures for each input in the GLTF PBR model. We then pack these according to the GLTF specification and place them in a model. And here is the result for the Omgänge bench. To the left, we have an offline rendered image, and the video on the right shows the resulting 3D model rendered in a WebGL viewer. The GLTF material is a metallic roughness-based model with a large set of material extensions to express effects such as clear code, anisotropy, sheen, etc. And throughout the years, new extensions have been added to the GLTF ecosystem. And so far, standard surface already have similar effects, meaning we only need to create a new translation to the GLTF version and bake them for our high-fidelity standard surface shaders. And since our articles is sold for many years, it's easy to update them to have as high visual fidelity as supported by the GLTF standard. So in short, we can reduce double work by leveraging translation graphs to create real-time versions of our shaders. And now, how can we speed up the workflow for an artist using translation graphs? OpenUSD is shipped with the USD Preview Surface Shading model, a fast, simple model used for preview of materials. And MaterialX includes the translation graph from standard surface to USD Preview Surface. And similar to GLTF, we can just translate to USD Preview Surface and then bake each input as a texture and pack them in the USD file. And for our models, we can then override the MaterialX material with these USD Preview Surface ones and use them as proxy materials in the viewport. This will decrease the cost of both loading a scene and interact with it. A baked preview surface shader are not as accurate compared to the standard surface shader. However, for simple materials, it's very good. And when rendering on the farm, we have structured our USD model such that the USD composition arc will make sure that the MaterialX standard surface variant of the materials are used. And here are some benchmarks showing the speedups we achieve when opening the USD scene with proxy materials. And most of the load time for us are due to large textures on the network. So we also have a material version using TX textures, which speeds up scene load a lot as well. But baked USD Preview Surface is still faster, especially when a user is interacting with the scene. And I will spare you waiting on the PNG version due to time constraints. And to conclude, translation graphs are great, and it helps us to define material once, and then pick the appropriate shading model for the job, leading to less work, faster iteration times, and also future-proofing our material library for evolving shading models. Thank you for listening, and I will hand it over to Arnon Marcus from OTOI.
I think you're muted, Arnon.
Sorry about that. So hello everyone, my name is Arnon Marcus. I'm a core developer in the Octane Render team at OTOI. I'm here to talk about support for MaterialX and OpenPBR Surface coming to Octane Render in 2026. A bit about Octane Render, in case you're not familiar with it. It is a spectral production renderer that runs on the GPU with broad industry support. It has plugins for many DCC applications, as well as standalone application, which I'll be showcasing in this presentation. MaterialX is coming to Octane Render starting from version 2026.1. This includes supports for importing materials from external sources, as well as for authoring shading networks manually using native MaterialX nodes in a new node set. The new set of nodes covers virtually the entire standard library of pattern nodes in MaterialX. In MaterialX, all nodes have explicit value types for both inputs and output. In Octane Render, starting from 2026.1, the material shading system supports all relevant value types for node inputs and output. Shading nodes may also provide user selection for value types for inputs and output. This improves shading authoring workflow in general in Octane Render and also unlocks first-class support for MaterialX. MaterialX defines node categories that group node types that do the same operation on different value types. In Octane Render, these are consolidated into singular node types with user-selectable value types for inputs and output. This minimizes the number of nodes in the new node set and streamlines the material shading graph authoring workflow. Connections can still be made across different types, resulting in implicit type conversions based on MaterialX convert node. As for importing, the new MaterialX importer supports many of the features of its native .mtlx interchange format, with just a few examples mentioned here. That said, much of the MaterialX content out there is actually in USD form. Octane Render already has a USD importer, and the two importers work together when importing MaterialX content from USD. This ensures feature parity when importing MaterialX from either format. Also coming to Octane Render 2026.1 is support for OpenPBR surface material. This comes as a physically based surface material node that can also be imported from external sources like MaterialX or USD. The material system in Octane Render supports layering and mixing of materials. Many of the surface materials in Octane Render already use this feature internally. Standard surface, for example, is internally a structure of material layers that are mixed and layered together according to the standard surface specification. And OpenPBR surface material just uses a different layering structure according to the OpenPBR specification. The specification focuses on the physical structure of the material components and how they interact, while leaving some room for implementations to cater to different kinds of render engines offering various approximations. Octane Render, being a spectral path tracer, can be more physically accurate and less approximate in its OpenPBR surface implementation. For example, thin film interference is a naturally spectral phenomenon in reality, so is well catered to by a spectral renderer. It can also be dialed in and out in an artist-friendly way in OpenPBR. And similarly, the dispersion effect can be scaled more intuitively. Thin-walled mode in OpenPBR has the subsurface slab allowing to dial between diffuse transmission and diffuse reflection. And the coat layer in OpenPBR tints the color of emission coming through it from below, controlled by the weight of the coat layer. Being able to dial these effects in and out typically comes at a cost, as presumably both options need to be computed and then blended. In Octane Render, however, this blending comes effectively for free thanks to probabilistic stochastic sampling as part of the Monte Carlo integration. Looking forward, OpenPBR full compliance is targeting 2026.1 for MaterialX, and we look into supporting nodes from more recent versions and potentially looking into supporting BXDF and PBR nodes for layering and mixing BSDFs. And that is all for me. I'll be handing off to Frankie from NVIDIA.
Morning. My name is Frankie Lipp, and I'm going to share what the team at NVIDIA has been doing with MaterialX and OpenPBR lately. So last year, we proposed the addition of a new set of infinite tiling nodes. In early versions of MaterialX, tiling is performed with regular grids, and this often produces repetitive artifacts, which limits our ability to produce visually plausible scenes with a lot of detail. This can be anything from large ground planes used for terrain to worn or scratched metals with fine micro scratches and blemishes. So a better technique is something called hex tiling, where instead of regular grids, we produce randomized hexagonal grids. And this technique breaks up obvious grid structures and results in a more natural, less repetitive appearance. The implementation we chose is based on a paper by Morten Michelson at Unity, and is designed with real-time graphics in mind. In the upcoming 139.4 release, we added 2 additional nodes, hex tile image for color textures, and hex tile normal map for normal maps. The method by Michelson builds on a by example noise algorithm that's adapted to reduce implementation complexity. And unlike other methods which use histogram preservation, this method favors direct blending of source texture tiles. For color images, it applies a contrast function to blending weights to maintain visual detail. And for normal mapping, the approach is well suited, as sampling the original texture is equivalent to sampling and blending with the partial derivatives of an implicit height map with respect to the tangent space normals. The nodes themselves are pretty intuitive. Besides the usual file and input texture coordinates, nodes have a basic set of tile, rotation, scale, and offset controls to control the randomization of tiles. You specify a range for each type of tile transformation, as well as a scalar amount. Blending of normal maps is controlled through a fall-off amount, and with color maps, there's an additional fall-off contrast control. So here's a side-by-side comparison. On the left is the current uniform tiling available pre-139.4, and on the right is the new hex tiling method. And here's what those tiles look like using a diagnostic texture. It works well for randomizing small detail scratches and blemishes. The normal map in this example is fairly simple, but it produces some pretty nice non-repeating detail when scaled up by many hundreds of tiles. Last year, we started work on an open source material library built on MaterialX. It's taken us some time to get this released, but we're happy to announce our new material library, Physical AI Sim-Ready Materials. The library is available today on GitHub, and it's released under MIT No Attribution. At NVIDIA, one of our goals is to enable simulation and validation and optimize through digital twins, so that companies can innovate and reduce risk and unlock efficiencies that aren't possible with physical systems alone. So for us, digital twins go beyond the visually beautiful 3D assets seen in games and movies. To us, they need to be true to life mirrors of their real world counterparts. So Physical Sim-Ready Materials combines the power of MaterialX to create visually compelling materials with non-visual sensor attributes for Sensor RTX and Isaac Sim. If you're not familiar, Isaac Sim inside of Omniverse is NVIDIA's simulation application for design, testing, and training intelligent robots in physically realistic virtual environments. Sensor RTX is our physically accurate high-scale sensor simulation microservice in Omniverse Cloud, and allows us to scale sensor rendering and simulation across hundreds of GPUs. Both Isaac Sim and Sensor Sim support the same underlying sensor models for things like cameras, LiDAR, and radar. And both can be used for simulation of things like autonomous vehicles and robots, and manufacturing, and smart infrastructure. So to enable this type of sensor simulation, materials in our SimReady library contain additional semantic information that helps influence the sensor models. The sensor runtime uses this information along with additionally defined physical properties to produce the correct sensor output. So here you're looking at one of our digital factories with a number of AI robots and devices processing parts as they move along through the factory floor. OpenPBR and MaterialX shaders produce the visual pixels on the screen, but non-visual semantic labels provide additional information to Sensor RTX. And so here you're seeing the segmentation information generated by the semantic data returned by the camera sensors. LiDAR sensors in the scene use this information along with additional information such as reflectivity and transparency and texture to reason and produce 3D point data. If we were using radar or thermal cameras, materials would convey information such as radio emissivity or thermal conductivity. And ultimately, what we want to achieve is a physically accurate standard for 3D assets for simulation. And as things continue to evolve, we hope to find more ways for the physical properties and attributes to find their way into MaterialX. So this library is the beginning, and it's our hope that this enables industries without traditional in-house look development or material expertise to easily incorporate realistic and physically accurate assets into their digital twin libraries. As part of our future work, something new that we're working on and we'd like to consider is a procedural flake node. Motivated by our partners in automotive, apparel, consumer goods, architecture, and aerospace, we're aiming to match physically measured appearances such as ASWF. Flakes are procedurally placed using grid-based noise for repeatability and randomness, and each flake is generated as a randomly oriented rectangular cube-like shape, creating sharp geometric patterns. Flakes can be overlapped, and each is assigned a random depth, ensuring clear visual ordering for a sense of layered structure. Total flake coverage is adjustable via a coverage parameter, matching real-world material samples, and each flake's normal aligns with measured surface roughness, sampled via microfast distributions such as Beckman, GGX, or Phong. For visual accuracy, we can set flake color from statistically drawn measured color data. And with this node, we think users will produce physically accurate, procedurally generated flake-based effects, suitable for high-performance digital twins and material simulation, with fine control to match both visual and physical measurements. We have other ideas for contributions, including finishing up a proposal for retroreflectivity. But if the community has other ideas and on how we can help improve materials, feel free to reach out. I can be found on Slack at Frankie Liu or via email fpliu@NVIDIA. And lastly, I'd like to give a huge thanks and acknowledgement to the contributions of my fellow teammates over the last year. They've been working incredibly hard to improve materials experience in Omniverse and find new ways to bring MaterialX to our industrial partners. Thank you for listening, and I'd like to hand it over to Ashwin at Autodesk.
Hi, is my slides okay? Right. Hi, I'm Ashwin. Thanks, Frankie. Good morning, everyone. So I'll provide a quick update on MaterialX and OpenPBR at Autodesk. Here is the Autodesk Safe Harbor statement that applies to the material that is shared in this presentation. Autodesk makes software for people who design and make things. So our product portfolio covers various industry groups such as architecture, engineering, and construction, product design and manufacturing, and media and entertainment. Across these products, we have a wide range of graphics requirements. For materials, our requirements range from simple unlit shading to realistic physically based shading. To meet these requirements, our main objectives are to use modern graphics API and leverage and extend open standards using decoupled architecture to ensure scale and continuity, and to support various form factors. So with that, here is an update on the products. For Maya, Max, and Arnold, I would like to share that in addition to the new improvements, OpenPBR is now the default material. LookDevX is our agnostic material editor and continues to deliver on the one shading graph, any platform and render promise. Please contact Nicola for additional details on upcoming new features and improvements. VRED is our visualization software for automotive and product design. It now has MaterialX support with both OpenGL and Vulkan backends, and also in the ray traced views. VRED is also available as a Hydra plugin. For more details, reach out to Andreas for more demos and details. For our AEC and manufacturing products, MaterialX is used in various viewport and data interop workflows. We make use of the MaterialX translation graphs for interop. Also, all legacy materials now use MaterialX with Autodesk standard surface. We will be evaluating OpenPBR in future. We are extending our material library to support procedural nodes that are required for AEC and manufacturing. These are real-world unit-aware procedurals authored using LibTevX, but compatible with MaterialX graph editor. They are built using standard nodes and can be rendered with Arnold natively. Here are some examples of knurl, checkers, and tiles that have unique attributes required for our customers. Next, I would like to share an update on the procedural wood textures. This feature was introduced in Fusion 360 about 10 years ago and later introduced in 3ds Max. We now have a MaterialX implementation thanks to some great work by Zealand. The procedural wood nodes also support various wood species and variations. Here are some examples. Note that the MaterialX implementation is not as full-featured as the one in Fusion, and we might continue to improve it. Moving on to other improvements. We use MaterialX in Autodesk in a standalone mode with UST and with Hydra 2.0. MaterialX performance is essential for its adoption for us. So we built test scenes that exercises MaterialX in Storm and discovered some performance challenges. This test scene does not use procedurals yet. After collaborating with people at ASWF, we made some few improvements to address some of these challenges. These improvements include lowering library load times, shader network optimizations, parallel shader generation, and caching at various levels where it's possible. We have been seeing great speedups and would like to explore more improvements in future. I would like to thank Jerry and Paolo for these contributions. MaterialX WASM and WebGL shader generator was introduced in 138.2. For 139, I would like to highlight this new contribution from Scott Brew that adds a WebGPU VXL shader generator. The VXL shader generator works natively with UST Web, and it can also be used with any WebGPU renderer that supports MaterialX. We have been also experimenting with animation nodes for MaterialX. Now, these are nodes that support interpolation over inputs, such as time. So you can vary the time input and it can update things. Now, here is an example that uses line nodes and animates them to create an hourglass widget. Notice that the lines are transformed and scaled as the inputs vary. And to conclude, just for fun, here is Fabi from Flappy Bird, built using MaterialX animation nodes. Enjoy.
I love that so much. Thanks, Ashwin. Let me just share a screen so that we can focus on questions that folks might have. Let's see. I think there should be a Q&A tab. I'm going to see if I can see it from this view. Hopefully I can. Yeah, I can. So if folks have questions, just put them in the Q&A panel if you can find it in your Zoom screen, and we'd be happy to answer them. Just while we're fielding questions, I want to highlight that there is a release candidate out there, 1.39.4, that contains a lot of the work that folks talked about today, including the new web GPU shader generator and a bunch of other improvements. So make sure to test that in your builds. We're going to hold the release candidate window open for as long as people need to do sufficient testing, but we'd like to wrap that up at some point after SIGGRAPH. any questions for our speakers? You can also, of course, join the ASWF Slack and ask questions directly there. If you have more detailed technical questions, that's probably the right place. Well, all right. Thanks so much to all of our speakers. Oh, we do have one question from Jonathan Hines Garcia. Will volumetric PBR materials be scoped to include haze and other mostly transparent volumes? Let's pitch that to Adrian.
It's a very good question. For materials that are almost transparent, like haze, like atmospheric effects, so far, we are not considering those for OpenPBR volume. So far, like in terms of scope, it's really very much like assets that you grab and move from scene to scene. So like large-scale atmospheric effects like haze, not so much, but like really right now, we're focusing on effects. But why not? Why not in the future?
Thanks, Adrian. We have one additional question from Joao. For Ashwin, does Autodesk have any plans or experiments on adding support from converting from legacy non-MaterialX nodes from 3ds Max and Maya to MaterialX nodes? Good question.
I can I'll have to follow up on that with the team and get back to you on that.
I can say that this is definitely something that we know is important for users, I'm talking specifically for the model EMS, the media entertainment products. And this is very, very important for us, being able to convert from legacy materials to modern MaterialX. So this is definitely something that's, yeah, super interesting.
Any other questions from folks before we wrap things up for today? Well, I want to say thanks again to our amazing presenters. This was a murderer's row of great presentations. Thank you so much to everyone who participated, and look us up in the Slack if you'd like to join the conversation or if you have additional questions about what we presented today. Thanks so much, everyone.